The Big Bang theory has lost some validity with the new information discovered by the James Webb Space Telescope. We just made a surprising discovery that is revolutionizing world physics. The recent image captured by this telescope has generated compelling arguments that have surprised experts, putting an end to much speculation. The telescope's most recent discovery is visually stunning and could transform our understanding of the universe. The discussion among experts that this image has resolved centers on the perception of the cosmos. The stunning image taken by the James Webb Space Telescope challenges our understanding of the universe. This finding addresses one of the main problems in astrophysics: the age of the universe and its rate of expansion. Scientists from different generations have been puzzled by this unsolved phenomenon and have carried out numerous studies in search of answers. Cosmologists investigate how the universe originated, how it works, how it has changed over time, and how it might end. In the last 100 years, great advances have been made in this field. The most widely accepted theory is the Big Bang cosmological theory, which holds that the universe has been expanding for roughly 13.8 billion years, starting from an extremely hot and dense state. The Hubble constant, which indicates the speed at which the universe is expanding, is used to measure this growth. However, determining how to measure the Hubble constant is not straightforward, and there are two main methods: local measurements and measurements of the early universe. In space, objects such as stars and Type Ia supernovae, which are used as standard candles because of their consistent brightness, allow astronomers to measure how far away they are and thus calculate the Hubble constant. As the universe expands at varying speeds over time, scientists can calculate the Hubble constant accordingly. There are two main approaches. One is the measurement of the early universe. Scientists use readings of the cosmic microwave background, CMB radiation, which was found in the 1960s as the afterglow of the Big Bang. This microwave energy comes from when the universe was only 380,000 years old. Astronomers can determine the age of the universe and its expansion rate by measuring the tiny ripples in temperature and polarization that are released by the CMB. However, there is a problem. These methods do not yield the same result. Local measurements indicate that the universe is expanding faster than the CMB data indicates. Scientists have been working hard to understand why the outcomes vary, to decipher additional mysteries of the universe. Further studies are underway. The differences in measurement indicate that we do not yet understand everything. This suggests there may be errors in one or both methodologies. But thanks to the James Webb Space Telescope, we can peer farther into the darkness of space than ever before, revealing elements, planets, and galaxies we never thought possible. Scientists hoped the data would help them calculate the Hubble constant. But the first wave of data has revealed unexpected findings that don't align with existing expectations. Could this information give us a new perspective on space? We may need to reevaluate our understanding of how the universe works. We could find forces and particles never seen before, or we may find that dark energy, the unknown force speeding up the growth of the universe, needs to be reconsidered. With each new discovery, our ideas about space evolve. For example, the cosmic microwave background radiation, discovered in 1965, was persuasive support for the Big Bang theory. Before that, scientists believed the universe would last forever, expanding at a constant rate indefinitely. However, new evidence to the contrary emerged in the late 1990s, when it was found that the universe was accelerating in its expansion. Scientists also learned about dark energy and its impact. Every time we learn something new, we test whether it fits with previous knowledge and develop new ways of understanding the universe. Without this process, the challenges we face in cosmology could not lead us to better understandings. Despite the complexity of this problem, it is also exciting, because it drives us to develop better instruments for space exploration. Scientists around the world are interested in this cosmological puzzle because everyone wants to know more about the universe. Most importantly, it demonstrates how science is always evolving. As we learn more about the universe's structure and age, tension is another concept that goes hand in hand with Hubble tension, referring to how matter is distributed in space. We use this information to model the structure of the universe and observe how it has changed over time. Some areas of space have many galaxies clustered together, while others are relatively empty. Scientists use different methods to determine the magnitude of this dispersion. One possible way to address this is to look at how different densities of matter, such as galaxy clusters, bend light from distant galaxies. This phenomenon, known as gravitational lensing, allows us to see the effects of dark matter, which does not emit light and is therefore undetectable. Scientists also analyze the cosmic microwave background, CMB radiation, the afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying information from the early universe by studying the Scientists at the CMBB can comprehend how the universe was full of irregularities when it formed, but this information does not match the large-scale irregularities observed in the current universe. The non-spherical distribution of gravity suggests that matter in the early universe was more uniform than it is now, as observed through gravitational lensing. This suggests that there is a fundamental component that isn't included in our interpretation, bringing us back to the mystery of dark matter and how it operates. According to Rice, he and his team were able to redefine their work thanks to the Webb Space Telescope and wanted to investigate whether a possible error in the Hubble Space Telescope's measurements could be the cause of this discrepancy. But the JWST revealed the identical deviations which are concerning. Somewhere between these two observations, there must be a fundamental flaw in our comprehension of the universe. Rice stated in a conversation with Astronomy magazine in the United States, "Using the new space telescope has allowed us to look deeper into the universe through its sharp infrared view and study cosmic distances with ever greater accuracy. Both dark matter and dark energy are mysterious components that make up a significant part of the universe. But despite being opaque, their nature remains elusive. Black holes have been the leading explanation for certain gravitational effects. There is growing interest in exploring how dark matter and dark energy might influence these cosmic phenomena. Let me know your opinion in the comments box. If you like the video, remember to like and subscribe, and many thanks for watching. I'll see you in the next one. Thank you." As scientists continue to analyze data from the James Webb Space Telescope, the foundations of modern cosmology are the subject of unprecedented scrutiny. The capacity of this telescope to observe distant galaxies from just a few 100 million years after the Big Bang has challenged existing models of how galaxies form. Contrary to prior assumptions, the early universe appears to have hosted more mature, massive galaxies than expected. These findings suggest that either galaxy formation occurred much faster than previously believed, or our understanding of the physics governing the early universe needs a fundamental revision. One emerging theory to explain these discrepancies involves modifications to the lambda CDM model, the current prevailing cosmological model, which includes cold dark matter, CDM, and a cosmological constant, lambda, representing dark energy. Some physicists suggest that dark energy might not be constant at all, but instead may change over time or interact with dark matter. This constantly changing form of dark energy, sometimes called quintessence, may account for variations in cosmic expansion rates observed at different epochs. Other researchers are exploring alternative models of gravity, such as modified Newtonian dynamics, MOND, or scalar tensor theories, which propose changes to Einstein's general theory of relativity at cosmological scales. These theories attempt to explain phenomena like the formation and lensing of cosmic structures without invoking unknown entities like dark matter or dark energy. While controversial and not yet widely accepted, these ideas highlight the growing willingness of scientists to question long-held assumptions in light of new observational data. The JWST has also opened up opportunities to examine the chemical, composition, and atmospheres of exoplanets, some of which orbit in the habitable zones of their stars. These studies may not directly impact our comprehension of cosmic expansion. However, they provide useful context for the evolution of matter, star systems, and the potential for life in the universe. The chemical fingerprints JWST detects in these environments may also provide clues about the broader distribution of elements in the universe. Another important piece of the cosmological puzzle is the nature and behavior of inflation. A very rapid increase of the universe thought to have occurred just fractions of a second after the Big Bang. The inflationary model helps explain why the universe appears so uniform on large scales, despite the vast distances between areas. But the exact mechanism behind inflation remains speculative. Various models exist, including those in which scalar fields are involved and quantum changes occur, but no one theory has yet been confirmed by evidence from observations. Most recent data from the James Webb Space Telescope may also offer new insights into the inflationary epoch. By studying the distribution and structure of the earliest galaxies, researchers hope to uncover patterns that support or refute specific inflation models. If anomalies are detected, such as irregularities or unexpected clusterings seen in the cosmic background, it could point to physics that goes beyond the standard model. In parallel, theoretical physicists are working on unifying quantum mechanics with general relativity, a goal that is still one of the biggest challenges in modern science. A successful theory of quantum gravity could fundamentally alter our comprehension of the universe's origins, including the Big Bang itself. String theory and loop quantum gravity are two major approaches, but both continue to be highly speculative due to a lack of direct experimental support. All of these efforts, whether observational or theoretical, point to one overarching truth: our comprehension of the universe is still evolving. The James Webb Space Telescope has not only deepened the mystery, but also given us the tools to ask better questions. As more data becomes available, especially from long-duration missions and complementary instruments like the Euclid Space Telescope or ground-based observatories such as the Vera Rubin Observatory, we may soon find ourselves on the verge of a new paradigm in cosmology. Until then, the tension between different measurements of the expansion of the universe and the significant repercussions of those discrepancies will continue to drive innovation, debate, and discovery in the scientific community. What lies beyond may not only reshape our understanding of the universe's past, but also its future.